Before studying the recursive parameter estimation algorithm, it's a good idea to take a look at the forgetting factor. The forgetting factor is a parameter and it is denoted by lambda, and the value of lambda is between 0 and 1. It should not have the value of 0, but it can be equal to 1, so lambda is somewhere between 0 and 1. So how to put this forgetting factor to the quadratic function? This is the place of the forgetting factor in the quadratic function, because as you have a look at the quadratic function, every other parts are the same. So y index I is the measured output of the process. Phi index I transpose contains the input data. The unknown parameters are in the vector of p hat. We are taking the square of it, we sum all the individual errors and we take the half of it. And there is another difference. The index here, so the upper bound of the sum, is not n, it is not fixed, it is k. The k means that newer and newer measured data are incoming, and the value of the value of k is increasing from measured data to measured data. So it's an increasing number from measurement to measurement. Have a look at to the new term lambda to the power of k minus I. So if we are here in the origin, in this case, the value of I is equal to k when we are in the last element of the sum. In the last element of the sum, the value of the index I is equal to k, and the k minus k is equal to 0. That's why we are going to get lambda to the power of 0. It's equal to 1. So the last error is weighted with 1, so it's an important value. So what happens before the last element of the sum, we have the value of I equal to k minus 1. In this case, k minus I, this is k minus I, is equal to 1. So the weighting factor is lambda to the power of 1. So in this case, this element of the error is weighted with a number which is less than 1. So it is not so important. So before this, we will have lambda squared, lambda to the power of 3, and so on and so on. And this value is decreasing. So if this value is 1, it is a smaller value, it's another smaller value, and smaller and smaller. This is the weighting of the error. So it's a good idea to remember. So weighting the individual error terms. How to put this to the vectorized form of the quadratic function? These lambda parameters can be put into a capital lambda matrix. This matrix is a diagonal matrix, so the lambdas are in the diagonal elements. Every other elements are 0. And in this case, this matrix is symmetric, so the transpose of lambda is equal to lambda. If we go back to the last video, we can remember this equation which I have written there, but there is a new term here. This is lambda. So I put lambda to here. All the other terms are the same. So next, if I try to make the multiplication here, I am going to get the second row. It's a good idea to check by yourself, because everything is the same as in the last video, but there are new terms of lambda in every element. Then we are going to do the same. The second and the third elements should be the same. Then we are going to get this equation, this formula, and again we are going to take the derivative of v according to p. So this is the gradient of v. It should be equal to 0. It's a vector again, so I take an underline. And then we are going to get two equivalent formula, two algebraically equivalent formula. The first one, this one, is the normal equation. The second, this one, is the solution of the normal equation. But in this case, we are not going to use the first one, but the second one, because we have got an equation for p, and in this case, we would like to solve it online. We would like to solve it with a recursive formula using the newer and newer measured data step by step when the k is increasing. And about this recursive formula, starting with this equation, we are going to give an algorithm for that in the next lecture video.